the what, sorry? Uh-huh. You need 4 people per buggy, right? Paying the price of 4. Mm. Okay, thank you, Dimitri. So now I'm going to be telling you about a third technique that you use experimentally, which is single molecule FRET or fluorescence. And then what I will do in this case is I will show some examples of things that you can do with this technique and also discuss a little bit the challenges and how you can go about them. Okay. So first thing, a little bit of motivation. Okay, so I don't have to discuss this picture here or anything like that, but the question is, from the point of view of theory and from the point of view of simulations, this is the kind of things, well, obviously something more complex than this, but this is what you care about. You have landscapes, you calculate, you do simulations, you project, you get these ideas, and the problem we have is experimentally, there is no way to get information about that. So for the experimentalist, it's almost like a, like a dream concept. What experiments can do, though, they can actually probe free energy surfaces. And if this is the most sophisticated experiments. Even this is not easy, but this is something that can be done. And the idea of using single molecule experiments is that, although I talked this morning a little bit about how you can get information about the free energy surface, you have a simple model, and then you do your experiments and you analyze them. When you do in bulk, when you do the single molecule experiments, you have more information to get from them. And here is a little bit of a list of things that you can do with single molecule experiments and especially fluorescence experiments, which is what I'm going to be talking about today. So the first thing that you can obviously do is to measure differences in free energy populations. Right? So in bulk experiments, you never measure populations, you measure average properties, and you determine the populations by fitting the data to a model. In a single molecule experiment, if you can resolve the states, then you can quantify how much they populate, and from there you can, get the free energies, right? And this is something, in a way, is a direct measurement, in contrast to what bulk experiments do. Another thing that single molecule experiments can do that bulk experiments do is to be able to look at the properties of the end states as you are producing a perturbation. There is some way of getting information like this from bulk experiments when the conversion between the two states is very, very slow compared to the time of measurement. And in that case, you can actually resolve them in time. But for the most part, especially for protein folding, in order to see how the native and the unfolded state change as a function of whatever perturbation you are using, could be chemical denatures, temperature, so on, the only way to do this is by single molecule experiments. Okay? And this is also interesting because from what I discussed yesterday and also a little bit this morning, you all know that when you're analyzing experiments, you have to do these baseline extrapolations to really far away. And of course, if you don't know anything about the properties of the state, these baselines could be completely wrong and the numbers could be off. Okay, so those are kind of basic things. I will show some examples of those two in a moment. And then I will focus a little bit more on something more interesting, which is looking at the free energy surface and especially trying to see whether you can get information about the barrier height, which is something that we can do in bulk, but here you can do it more directly, and eventually to look at dynamics and folding transition paths. Okay, so the idea here is that can try to get information about how high this barrier is from the population in here. You can resolve it, or you can also look at the kinetics by seeing, the dwell times in the states. I'm going to talk a little bit about that, and then you can get information about the dynamics from the transition paths. And if you can measure for the transition paths, you can get the spread factor, and then with that and the kinetics, you should be able to get the surface. That's kind of the idea. Okay. So the technique that we are going to use to do single molecule experiments is fluorescence. So some very basic stuff about fluorescence. So obviously here the idea is, you have a fluorophore, which is a molecule that emits fluorescence, which means you can have a singlet state in the ground state. You can stimulate it by absorption. It's in the singlet state, then it's going to relax to some degree vibrationally over here, which is this. So this is non-radiative, right? And then you will relax all the way down to the ground state by emitting a photon. This photon is typically shifted to the red because of this conversion here. And that's what fluorescence is. The time scale for this process is on the order of nanoseconds. Okay, and changes from fluorophore to fluorophore are not very far from there. Okay, so obviously in proteins you have intrinsic fluorophores like tryptophan and tyrosine that you can use, but if you want to do single molecule experiments, you cannot really use those because the main property for a fluorophore is their quantum yield, which basically is how efficiently they emit a photon. So how many photons they absorb, how many they emit. The quantum yield for these guys is typically in the 10% or so they are not very bright. And also, their absorption is small. So the low absorption coefficient they have makes them not proper for single molecule experiments. So if you want to do single molecule experiments, you have to go into something like this, which is you have to use extrinsic fluorophores. So you have to put the fluorophore into the protein. And you can do this by chemical tricks. These fluorophores, you can see they are way bigger. They have multiple rings and are much more complex. That means they emit in the visible rather than in the UV. You can see the colors. They also have very high extinction coefficients, which is important because you want to make sure that the cross section for absorption is high, so because you will have only one molecule in your measurement volume. And also they have typically very high quantum yields. The closer to 1, the better. So there is one parameter that is actually the product of the extinction coefficient times the quantum yield, which is the brightness of the fluorophore. And the higher the brightness, the better, okay, especially for single molecule. Okay, so once that you have these fluorophores and you have means to put them into proteins, which we do by chemical modification, then what we're going to be talking about is to do forced resonance energy transfer. This mechanism is a dipole-dipole interaction. It's very similar to the NOE effect in NMR. So I was talking a little bit about this morning. So in principle, the idea here is that you have one fluorophore, which is called the donor, and that fluorophore is directly excited. It goes into its singlet state, has this vibronic relaxation here, and then it can do two things. It can actually emit a photon back, which is what I was telling you about before, or it can actually also, if there is another fluorophore nearby, that can be an acceptor for FRET, then there is a dipole-dipole interaction, so the energy is transferred from the excited state of this fluorophore into the excited state of this fluorophore, and then this fluorophore relaxes and emits. And of course, there is another loss of energy here, so that means that this fluorophore emits more to the blue, and this one more to the red. Okay. So the interesting thing about this process is that it's in a way dependent on the distance, and that's very useful when you're trying to do protein folding experiments, because one of the things that change with protein folding obviously is distances. So you can imagine putting two fluorophores at the ends of the protein so that they are not interacting with anything. So when the protein is folded, these two ends will be close by, so they will be very high FRET. So you will see mostly light coming from the receptor. When the protein is unfolded, these distances will be larger on average, and therefore the process will be less efficient, and then you will see mostly the green fluorescence. Okay? So this is the idea, in short, that you've seen this 100 times. But anyway, the important thing here to remember is that this parameter that is key here is the efficiency of the transfer process, which is proportional to the inverse of the distance to the 6th power. And the 6th power comes because it's a dipole-dipole interaction. Okay, so that's what this means. So because you have the 6th power dependence on the distance, which is here, you have also this parameter called R0 that tells you how efficient your pair is. And this parameter depends on the optical properties of the two dyes. And you have one of the important parameters that determines this here is this J, which is the overlap integral, which is the overlap between the emission of the donor and the absorption of the acceptor. Okay, so the larger this overlap, the larger is this R naught, which means that because that's what this defines, is the distance at which the energy transfer process has 50% efficiency, right? Which is this here. So the larger this R naught, the more efficient is the process because you actually get 50% transfer at longer distances. Okay, so very simple. This parameter depends on many other things. This is the quantum yield of the donor, refraction index, obviously, and then this other parameter, which is the orientation factor, this kappa square, which has to do with the dipole-dipole interaction, transition dipoles for the two dyes. So depending on whether they are parallel, orthogonal, or they are dynamically averaging. Most of the times, when the dyes are free and not fixed in one particular configuration, for example, when they're at the tails of the protein, you assume that this kappa square is actually 2/3, which basically implies assuming that there is dynamic averaging. So the dyes have time to rotate freely in the 5 nanoseconds, typically, that it takes to emit. Another important thing here to discuss is that because this is 6 power dependence, the process is very sharp. So that means that you have a window of distances that you can actually resolve, right? So if your R naught is, let's say, 1, here you will be able to see things that are, changes when the distance is like half of that or twice that, and that's the window that you have. Anything beyond or shorter, you won't be able to see a difference. What that means is that, the designing where you put the dyes issue. Sometimes you are luckier than other times, and you get a better signal response or worse. Okay, so this is the fluorescence part. Now, if you want to do single molecule experiments, what you have to do, there are different ways of doing this, but I'm going to talk about just one, which is using a confocal microscope. And what is a confocal microscope? It's basically a regular optical microscope that it has an objective that has very high numerical aperture, which basically means it focuses into a very, very small volume. And that volume is actually selected by a pinhole, which is the one that produces the confocal effect. So in the end, you end up with something that looks like a Gaussian volume that is as small as a 1 femtoliter. So it's very, very small. And of course, that's important because that way you can localize individual molecules. And you can do the experiment in different ways. You can do it by having molecules that are freely diffusing, or you can tether the molecules to the surface and then look for different molecules and look at them. All right? So that's the way you achieve single molecule resolution. But of course, you need to have ways of detecting that molecule. So normally what happens is you use this illumination volume to excite the fluorescence, and you also use it to collect the fluorescence, to excite the molecule, and you also use it to collect the fluorescence back. So, normally you excite, and then you collect through the same objective, okay? Which is what you have basically here. You can see you are exciting this way, it's coming, and then, you're exciting this way, and then the fluorescence is coming this way back. All right? And then the other thing that you need is these detectors, which are detectors that are able to detect single photons. Normally, detectors that people use nowadays, they are called SPADs. And then you can also use different types of detectors. So there are detectors that are able to detect single photons, and they do this with picosecond resolution. Okay. And then what you need also is a whole bunch of electronics to make sure that you do the single photon counting. So you know exactly when you get a photon. You can differentiate the color by putting filters and having multiple channels. You can also detect polarization, so you can do all these things. So in principle, you can see when every photon that comes into here, you can detect it, color, polarization, and time of arrival. That's the kind of information you get. Okay. So normally, in the most basic representation of this, you have your molecules that are, diffusing around and passing by here, and when they do, they will be excited, they will emit fluorescence, and then you will get a trace as a function of time that looks like this, in which basically every event in which a molecule passes, you will see as a burst. And this burst will have photons from the donor and photons from the acceptor. Okay? These bursts will typically take on the order of 300 to 400 microseconds to go by, because that's depending on the diffusion coefficient of proteins, that's the time it takes then on average to go through here. Okay? So that's the time window you have when the molecule is not tethered. If the molecule is tethered, you can actually look at this for as long as it lasts. Okay, so this is what I have here. There are different ways of doing the experiment. I say the simplest one is you have the protein labeled with the 2 fluorophores and it's free. So, and when it passes by, you see it. You have other chemical ways of immobilizing the molecule. So you can actually tether it through a streptavidin biotin kind of trick. And then you put the protein sufficiently far away from the surface so that it doesn't interact with it, but still close so that you can detect it. You can also do the same thing using a liposome and embedding the protein in the liposome. This is not to scale, by the way. Okay, the liposome will be way larger than the protein compared to this. Okay, so all of that, I'm sure you know. Now, the question here is, the analysis of this data is more tricky than it seems. In principle, it seems very simple, but there are lots of implications. So normally, as I said, you have a basically what is called a count rate. So you're counting photons as a function of time, right? So this time, these counts, you can bin them. So say, I'm going to collect all the photons every 20 microseconds or so. And this will have 20 microseconds resolution. And then what you do in order to calculate the FRET, or the forced resonance energy transfer, is to do something like this, rather than using the formula that I used before for bulk. In this case, what you say, I can simply get the same number by counting how many photons from the acceptor I see, so how many reds, versus how much of the total, which is red plus green, okay? And you can work the math. Basically, in principle, it's equivalent, right? So this seems like a very simple measurement to make, right? An analysis. Now the problem is obviously because we are talking about a very limited number of photons. When you do a bulk experiment, you have tons of molecules and you get lots of photons. Here we have a single molecule, and we are getting a finite number of photons, which means basically these photons are emitted following Poisson statistics. And what that means is that the accuracy which you can measure them depend basically on these shot noise statistics. And the formula to define that is here. And this is coming from Attila Szabo and Irina Gopic, which have done all the analysis for these things. But in principle, you get histograms that look like this for a two-state system, right? You have an unfolded state and a folded state, but they are broad. And in principle, the first thing you would imagine is, okay, they are broad because you are seeing the shape of the surface. The fact of the matter is that on top of any feature like this, you have this shot noise, okay? And this shot noise is quite big. For example, for a FRET efficiency of 0.5, this will be 0.25. And if you are measuring 40 photons, for instance, which would be a relatively good number coming from one molecule, then you will determine these peaks with a standard deviation that is close to 10%. So, really pretty broad. So what that means is when you get something like that, there is all this shot noise. And of course, the shot noise analysis here is based on a constant number of photons, but when you have freely diffusing molecules, sometimes you will get more photons, sometimes you will get fewer photons just because the molecule is following a longer path or a shorter path, or is closer to the center, the focal point, or is a little bit on the sides. Okay, so all those things are kind of important. Anyway, so I'm going to talk a little bit about how to use this type of analysis, which is the conventional one, to do something interesting in folding, and then I will move into something else. Okay, so these are some experiments, and here what we're trying to do is to look at a slow folding protein, nothing like what I was talking about this morning. In this particular case, it's alpha spectrum SH3 domain. It's a slow folder, folds in seconds, and it's supposed to be a model for two-state folding, even though it's quite small protein. It's the same size or a little bit smaller than the one I was talking about this morning. So what you do is you put the dyes at the ends, as you can see here, and then you can look at the FRET. And what we are hoping to do here is, because this rate of conversion between folded and unfolded is very slow, we should be able to resolve the two states separately, and we would like to see what the properties of those states are, right? So this is one of the first applications that I was mentioning before. So the idea is that if we have a surface like this, and then upon perturbation, this minima shift in position, which is something that you should expect to see in a way, you are going to be able to measure them, okay? So that's kind of the rationale of the experiment. So the first thing that you need to do when you do experiments is to check that your dyes don't make a mess, right? Because you can see there are big molecules compared to your protein, right? So they are not trivial perturbations. So the way you can do this is by measuring the unfolding process using chemical denaturants, for example, for the protein when it's unlabeled, and for the protein when it's labeled. And these are bulk experiments. And if they look the same, or very close to the same, then you can safely assume that the process is fine, and what you are going to see in the single molecule experiments reflect what you see in bulk with unlabeled protein. Okay, so now you can collect the photons, do these experiments in the single molecule instrument at a function of urea 1-edinium. And what you can see here, I'm showing both. By the way, I didn't mention this, but you can see that the scale here is different because urea is a much weaker denatural than 1-edinium. So the ratio of conversion is around 3 again. But they look the same when you convert for the different strengths. And here what we are doing is trying to look at both the naturals to see that the effects that we have are not the natural dependent, so that you see them in both. And what you can see, obviously the strength is different. This value is still a little bit less than this, but it's close. This is equivalent to something like 9.2 molar urea. Okay, but the important thing here is this is the native state, and you have it in both. And you can see that as you start adding the naturant, this peak is decreasing in amplitude, so because the protein is unfolding, but also is shifting. So you can see that the position changes, and you see it in urea. You also see it in 1-edinium. Okay, and then this other peak that is coming up is the unfolded state. And obviously, when you go to a lot high denatural concentrations, you only see this one. So this is what you can get populations from this experiment. But you can also see that in addition to populations, you can also see that this unfolded state is becoming more expanded as we go to higher denaturant. Okay, so the properties are changing, and they are changing this way. Here I'm just plotting the flare efficiency for both states. The dashed line corresponds to what the unfolding bulk experiment would be. What you can see here is that the unfolded state is expanding a lot and is following this pretty sharp curve. And this is something that many people have seen before, so this is not new. What is kind of a bit more new in this experiment is that we also see the native state to change quite significantly, right? And what that means, obviously, is that when you're doing bulk experiments, you have to be careful with these baselines, because normally you assume something linear, you will go here, you will go there, your populations are going to be off. And that's what it shows here. So what this plot is a delta G of unfolding calculated by integrating the areas of those two peaks and calculating the probabilities from their populations, and then converting into free energy. Those are the dots, and the line is the fit to it. And the thin black line is what you actually assume there is from the bulk analysis. Okay, so what you can see from this is that the real populations obtained from single molecules are a little bit, are fine, and that the free energy is actually a little bit weaker in native conditions that you will get from the bulk experiment. Because in the bulk experiment, you're extrapolating. So that means that in bulk experiments, you typically, this is true for other proteins, you typically overestimate the stability of the protein. Okay? All right. So another thing that you can do with this is try to look at this downhill folding business that I was talking about before. And we are going to use the same type of analysis in a way. And this is the protein that I discussed this morning briefly. First protein that was identified to be one-state downhill folder. And we wanted to do single molecule experiments to see how they behave, how the protein behaves. And now the problem here is we would like to distinguish within these two possibilities. And in principle, you would say, okay, single molecule experiments, Fred experiments would be ideal for this, right? Because in this case, what you have is a change in populations of two minima that are on the streams. And in this case, what you have is a single ensemble of population that is moving, right? So it should be really easy. But it turns out that it's not so trivial because the dynamics of the system play an important role here as well. So in this case, for example, if your meaning time, which is the time at which you are collecting photons to do the analysis, is actually shorter than the time for relaxing the kinetics of folding and unfolding, then in that case, this scenario will produce what I said, a peak here in these conditions, a peak there in those conditions, and in these conditions, you will get two peaks. Are going to be a little bit shifted closer from the effect that I just showed, but in principle, the populations will be 50-50, okay? But if this binning time is actually much larger than this relaxation time for the process, what you get is dynamic averaging. It's the same effect that I was talking about for NMR. So rather than seeing this, you will see something in the middle, which is exactly what you're expecting to see in this case, right? If you look at this one-state scenario, the main difference that you see is, say, this continuous shift, but you would only see it if your time resolution is much better than the relaxation time of the molecule. And this happens to be a problem because, obviously proteins that are downhill folders are also fast folders. And the fast folding means that you have limitations in the technique. And you can see what that means practically. These are some simulations, some stochastic simulations of histograms for this scenario, coming from a model like this and from this scenario, which you basically have over here, over there, and over here. And what you can see is in the two-state case, if you have very high resolution, because the relaxation rate in the simulation was 250 microseconds. So this is faster. So here you can distinguish the two peaks well, even though there is still a little bit of crosstalk. And these are molecules that actually happen to have time to go from one state to the other while you're making the measurement. Okay? And as you go to longer times, like 1 millisecond, this becomes a single one, right? And in this case, you see also changes, but the changes are not so drastic because you are only, you are going from here to there. This is like from here to there. Okay? So this is the big issue. So now let me tell you a little bit about why is this problematic for single molecule fluorescence experiments. The problem is we have a theoretical limit of about 2,000 photons per millisecond that we can measure with this technique. And the question is, why is that? Well, this comes from a variety of reasons. The first one is the maximum number of photons you can get from one molecule comes from exciting the molecule all the time and collecting the photons all the time, right? So the lifetime of fluorescence for these dyes is about 5 nanoseconds. What that means is that the fastest you could ever get a photon to come from a molecule is every 5 nanoseconds. So that means that emits 5 nanoseconds, you excite it again, emits another one, so on and so forth. Now, that will be much more than 2,000 photons per millisecond. But, the instrument has huge losses. And that's what is not so obvious. You can see one of them clearly here, which is, this is a representation of where the objective would be. Your molecule is going to be floating. This is the confocal volume. So normally, you excite this direction. But, of course, the process is anisotropic, so the emission could come anywhere in this sphere. And you are only collecting through this solid angle. So your collection efficiency from just this effect is on the order of 25% maximum. And that's very hard to get. Okay? So that's the first loss. And then obviously, on top of this, you have all this bunch of lenses and filters and so on. Each one has losses. Then the detectors have some sensitivity, which is not wonderful, and so on and so forth. At the end of the day, when you put all these factors together, your collection efficiency is on the order of 2%, which means it's a crappy instrument in a way. But of course, you're trying to do something really difficult, all right? So out of this 1 photon every 5 nanoseconds, you're only going to collect 2% of those. And that's, where these numbers, maybe, you're lucky, maybe 3 or 4%. You're playing with the optics and with the mirrors and with the alignment and with all these different things, okay? So this limit obviously is a problem because I told you before that with fewer than 40 photons, it's very hard to measure any threat with any, even decent accuracy, right? So that's a problem, but the problem is actually even harder because this is the theoretical limit. In practice, you never get anything close to that. Why is that? Because these molecules have this nasty habit of becoming bleached or blinked, right? And this happens because there is a lot of photophysics going on, so you are exciting the molecule, and especially you are trying to get as many photons as possible, you are banging it away here. Putting a lot of intensity. What that means is basically, rather than doing this all the time, sometimes you're going to go into triplets. Right, doing this, you're going to go into triplets. The triplets are very long-lived. A triplet doesn't have a lifetime of nanoseconds. It has a lifetime of microseconds, sometimes even milliseconds, which means every time that you go into here, your molecule is going to be off for a very long period of time. Let's say maybe 100 microseconds, so you don't see anything. Of course, this is a low probability event, but since you are exciting the molecule so many times, eventually happens, right? So this is just, your odds are not good for that reason. And also, on top of this, if you have contact of this triplet with some free radicals like this, then you can bleach the molecule. And the molecule gets photo-oxidized or things like this, and then the molecule doesn't emit anymore. And this means the molecule is gone forever. Okay? That's not so much of a problem from the point of view of analysis, because when the molecule dies, okay, fine, you get another one, right? The problem is it limits for how long you can look at your molecule. Right? This problem is a bigger problem from the point of view of trying to get a very high collection efficiency, because the more you try to get, the less you get. This is the perversion of the system, right? Because the more intensity you put to get more photons, the more triplet you make. Okay, so you have to play a little bit with this photophysics. It's not something interesting or attractive for many people, but it's important. So in our case, we looked at some combinations of things that we could do. And the first thing that we found here, I'm just not going to tell you much about this because probably you don't care, but most people were actually doing these experiments trying to eliminate free radicals to try to reduce the bleaching. Okay? And the way to do that was to actually try to remove oxygen from the system. When they reduced the oxygen, things worked from the point of view of bleaching, but oxygen is the best triplet quencher there is. So the problem is you were getting no bleaching, but you were getting too much blinking or triplet formation. So you couldn't go into high collection efficiency or high photon count rates. So what we did is a different trick. So we added as much oxygen in solution as possible, and then we used radical scavengers to get rid of the free radicals, but still keeping the oxygen. And by doing that, we could actually get improvements in the photon collection efficiency of the order of factor of 20. So big effects. I'm talking about little things. And by doing this, we could actually find conditions in which we got very close to 1,000 photons per millisecond, which is about half maximum in principle. Okay, this is still not good enough because this protein BBL at room temperature folds and unfolds in 20 microseconds. So you can see that there is no way you can collect 40 photons in that period of time, right? Actually, faster than that. So one other thing that you can do is, okay, maybe you don't have to study the protein at 20 degrees. You can go to lower temperature. The process gets slower. This is a very simple trick. So that's what we did here. So we put the protein at 5 degrees rather than 20 or 25. Now your relaxation is on the order of 200, so it's 10 times slower because folding is very temperature dependent, especially in this range. Okay. So now we are a bit, now we are getting close, because if you think about 200 microseconds relaxation, and we have 5,000 photons per millisecond, we could do time beams of 50 microseconds, which will be shorter than this, and in those we will get close to 50 photons, which should be doable. Okay, so these conditions allows us to do this experiment. This is the protein with the labels, unfold the state. This is the control that the dyes don't seem to do too much bad to the protein. And these are the experiments. In this case, urea is shown in blue and guanidinium is in green, but the guanidinium is used to go to the highest denaturing conditions possible. We want to use urea because the photophysics are better in urea, but the urea is not a strong denaturant enough because you can only go to here, and then we need the guanidinium to complete this, right? But in this experiment, what you actually see is we have 50 microsecond beams. The photon beams, the photon threshold we used for the beams was 45, so that means that we had relatively good accuracy in the FRET. And what we could see is that in going from native conditions to re-unfolded conditions, we saw a single peak. By the way, this is coming from blinking. Okay, this thing at 0 is an artifact that appears because when the molecule is blinked, normally the one that is blinked is the acceptor, because it's the one, the donor has a very short lifetime because it's always transferring. So the one that gets blinked is the acceptor. And when the acceptor is blinked, the molecule looks like it's only donors, it's only green. So it looks like 0 FRET, right? So that's a very well-known artifact. Anyway, going back to the experiments, we could see that the protein is basically shifting, and it's more clear with the line, you can see. And this is corresponding to the midpoint, so it's halfway, and then it keeps shifting, and there is no sign of two different populations and shifting or everything like that. But of course, even with 50 microsecond beams, we are only 4 times faster than the time scale for the kinetics. So we had to do a little bit more of analysis. And what we did here is something to take into account the possibility of conformational exchange between the two molecules, between the two states. So this is the histogram that you get, I was showing before, at the midpoint. So this is the 6 molar urea one, okay? So those are the bars. So you can see that it looks like a single one, but also because you have a little bit of distortion due to this blinking happening once in a while, you could also fit it to a two-state model with two peaks that are very close. That's the blue line, right? And this line seems to be, almost looking like a single one, because even with 50 microseconds, and we are using a photon threshold of 60, there is some probability that the molecule will go from one to the other, and that probability is defined by this Gaussian curve here. And when that happens, obviously your FRET is mixed, and then you get something, rather than these two peaks nicely separated like here, you see things merging together, all right? And in principle, even though it looks like a one-state system, we couldn't really tell from here, but the interesting thing is, even though you are going to longer time beams here, going from 50 to 100 and 100 to 150, the increase in the photon threshold, because you have basically longer time to measure, is actually more important than this, right? So this produces more dynamics. So you see the amplitude of this black curve getting larger. But at the same time, this photon threshold makes the peaks better defined. So you can see these are broad, these are narrower, right? So when you go to 150 microseconds, you can use a photon threshold of 145. So now you can get these peaks with very high resolution. So you can see much more clearly that in these conditions, in a two-state system that fits this data, you should see a very clear different peak here, which you don't. So what this means is, when you do histogram analysis, you always have these dynamic effects in there and the shot noise effect in there, and you have to take care of that quantitatively to be, to make sure that you don't make a mistake. And this is obviously hard to do. And so this is in a way as far as you can go with this type of analysis. So we need something else, okay? And what we decided to do is to use the analysis of photon arrival times using a maximum likelihood analysis. And this is a technique that was developed by Attila Szabo and Irina Gopic. So we just borrowed it. And let me just cross this. And here the idea is the following. Here. Sorry, here. Okay. So now, rather than binning, and basically which means you take all these photons together and you separate them by green and red, and you calculate the FRET. Now what you can do is say, because the number of photons that I'm going to get to see is not enough for the processes that I'm interested in, like folding transition paths, which may take a few microseconds, so it's going to take only a few photons to see. Then what I can do is something different, which is, rather than doing that, as I said, what I can do is look at the times, which is another information that I get from these experiments. So I can get the color and the arrival time. So I can get a sequence of a photon trajectory or a sequence of colors and times, which is what you have here, okay? And then what I can do is I take this data directly and I perform a maximum likelihood analysis and see what would be the most likely process that is giving rise to the sequence, okay? So the problem with this kind of method is that in order to do this, you need to have a model. So back into the modeling rather than direct analysis, and this is the problem that you have here. So you can calculate the likelihood of any particular model once that you have it, and this is what I have here, is a kinetic model, it's a rate matrix, right? Provided that you have basically all this photon information and you have an equation like this. So this is how it works. So let me just show it to you for a two-state model, which is easy, but the concept is the same for something more complex. So as I said, it's an analysis that requires to have a model. So the model could be that the process is two-state, and then your parameters will be the rate constants. So this is the rate matrix, right? So from U and F, so you have the KU and the KF. This is the diagonal, tells you, the disappearance of the species, and this is the emergence of the species. And then what you do is you define also a matrix with the FRET values for the different species what is the probability for emitting an acceptor photon, which is basically the FRET efficiency of the photon, of the state, right, which is what I said before. And then you can do the same thing for the donor. So these two are predefined. So you need to know what the structure of the protein is in the native state, so you can calculate the expected FRET, which will come from here and there, right? So these are predefined. Then you will have the probability of being native and unfolded at the conditions of interest. and then you have this rate matrix. And then the probability, the maximum likelihood for any particular two-state model, which means any particular set of these two coefficients that also determine here this, will come from this particular expression. And the way you calculate it is like this. So let's say that you have this sequence. It's really simple, right? So what you do is say, okay, my first photon happens to be an acceptor photon, is red, right? So then what I had to do here is to plug here the Fred efficiency, which corresponds to an acceptor photon, multiplied by the equilibrium probability, because we haven't moved yet, right? Now, if I wait this time, which is tau 2, now obviously my system can interconvert according to the rates coming from the rate matrix, right? So, and what I see is actually a green photon. So now what I have is I multiply in this, which is my first photon, times this, which is the Fred efficiency, 1 minus the Fred efficiency, which is the probability of emitting a green photon, times the probability that I have to interconvert from here into there, which is defined by the rate matrix times the time, okay? And then I do the same thing for the third photon. Now I see the third photon is actually red, so I go back to E rather than 1 minus E, which is the probability of emitting an acceptor photon for both species, times again the rate matrix times tau. And I can do this one, for another red photon and then another green photon. And of course, this is only for 5. The idea is that you do this with thousands of photons. And in doing that, in the end, you can compute the likelihood. And the only thing that you need to do now is you can calculate this for any particular model, and then you can fit the parameters to make sure that this is maximized. So what you do is you find the best model that produces the highest probability for this photon strip, the photon trajectory to be coming from it. Okay? Is that clear? Good. All right, so this is what happens. As I say, the limitation is that you need to have a model. And this is a two-state model. This is something that actually Eaton uses as well. He normally uses this two-state model to try to determine the transition paths. And the only thing he's interested in is the times. Okay. We wanted to do something a little bit more elaborate. And the idea was to try to extend this model into this analysis, or into some model that is more flexible. And you can probably guess what kind of model we wanted to use again, which is the same one that I introduced already this morning. It's this model that is a free energy surface, one-dimensional model, and all these things, which the equations are here. The nice feature about this is that you can actually modify the barrier height and the position of the minima according to the parameters. It has the same number of parameters that a two-state model, but it gives you much more, because in principle the same model, depending on the parameters, can switch from being one state to being two-state, or being something in between. Okay. So then we can do. The idea is to combine this model with this type of analysis and with the photon arrival time data that we can get from the experiments, and see whether by doing this together we can find ways of finding the most likely free energy surface for a given experiment, and also the dynamics as well. Because we get the dynamics here by assuming this is by free diffusion. I didn't talk much about this morning, but in principle is diffusion over this landscape in a way. Okay. So I'm going to go quickly through here. So this is again the same model I showed before. And now the only thing that you need to do is, rather than putting this 2x2 rate matrix, now you put this one with n by n, in which each particular position here is one of the points of this free energy surface. So you discretize the free energy surface. Let's say you divide it into 100 points, and then you define a rate matrix like this, which is diffusive. That's why these funny terms come from. They are not jumping rates, they are diffusive, right? Which means that you have a diffusion coefficient, and it depends on both. It takes into account the possibility of actually sliding through the surface rather than jumping. Okay? So what you do now is you take this kind of rate matrix and you plug it into this, and you do the same type of analysis. Okay? So of course, we wanted to make sure that this is useful. So the first thing we did is check with simulations. And the simulations that we do are using the model. And in the model, we define these 3 scenarios, which are string cases. And now what we can do is, in this case, we have a 4 KT barrier. This one is 1, which is similar to GPW, and this is similar to BBL. Right? These are the probability distributions that the model gets. So now we can do stochastic simulations of this kinetically using the rate matrix. So we can actually do a simulation of what a molecule would do. We can also put the photon emission numbers into that, and then see whether the analysis can retrieve back what you put in. In this case, we know the answer. And what we're trying to test is how the how the procedure works, right? So you do the stochastic simulations. This is the way they look like. For this case, it's not really two-state. It's two-state-like because you can see there is still a little bit, because it's 4kT, so there's still a little bit of probability there. But you can see that this looks like a switching function, so like what everybody would think is two-state. If you go to this case, still looks quite switching, but you can see also trajectories in which the molecule goes to the barrier top and then comes back, or which are these kind of things. So the molecule is going over here and then back and so on. And then when you go into the scenario, the dynamics are purely Brownian. So it's nothing, these are basically Brownian dynamics, okay? So this is, as I say, all simulated. We know what it is. So now what we can do is take this data and simulate the photon emission statistics. We can introduce noise of different kinds and see how the procedure works. So this is some summary of some of these things. For example, here, this is for the two-state scenario, for the marginal barrier, and for the one-state. And what we are checking here is how many photons we need in order to get a good determination of this. So what you can see here is that when you use only 10,000 photons, which is still many trajectories together, you don't get a great agreement because the parent, so the original distribution is the green one, and what you're getting is the red one. But what you can see is you're getting the red one not because the procedure is not working, it's just because your statistics are not good enough, because the red is in very good agreement with the black. It's actually the real probability that you get from the 10,000, from the tiny text to get 10,000 photons, okay? And you can see it here as well, and here as well. So what that means is the procedure works well, it's just that you don't have enough photons to get good statistics for folding, okay? So when you go to 50,000 photons, that means you have 5 times more data. That means now your parent and your experimentally simulated distributions are more similar, and the calculations seem to work much better. And when you go to 100,000 photons, then the agreement is really good. So the system seems to be, the procedure seems to be working. We can also retrieve back the parameters that we put in with very high accuracy, which means it works. All the simulations were with no noise, but you can also do simulations adding noise. And this is the type of white noise that you get in these experiments. And what find is that this kind of analysis is very robust to noise. Okay, and you can see it over here. You distort the histogram quite a lot by introducing noise, which you can see the black compared to the green. They're very different histograms. Even so, when you do the analysis, you actually get something that is almost identical. So this maximum likelihood analysis is able to get rid of the noise because it's not correlated, and therefore, when you do the analysis, it kind of goes away. Not completely, but to a large extent. So that's good. So we tried many other tests, but what this tells us is that this is a good method to try to study protein folding experimentally and try to get the free surface information. One more thing that is important, and I didn't quite say, and it's the most important result actually, is that in contrast to what I was saying for the photon binning, this analysis is not dependent on on the relaxation time of the process. And the fact of the matter is here, and remember, in this case, we are simulating a surface, and the molecule could be in any position around. So basically, it's diffusing and jumping back and forth. And what we are finding here is that the performance of the analysis is actually good, provided that your interphoton time is is not longer than, let's say, a tenth of the relaxation time. So now we don't need 50 photons per bin. We need like 10 photons. With 10 photons, we can actually get the same type of information we were getting with 50 before. What that means is, obviously, practically, we are increasing the time resolution of this analysis by a factor of 5, just by doing this. And we are also handling noise much better because we have a clear way of weeding it out. Okay. So now let me just show you some experiments. This is unpublished, but quickly because I don't have much time. I would like to finish before time. So anyway, what we looked at now, not a slow folder like before. We're looking at this other protein called Engerel homodomain, which is an alpha helical protein with 3 helices in a bundle. We have studied this protein folding-wise with all these techniques that I described this morning. And it looks also like another downhill folder. At the midpoint, it has a very small barrier, which is half a kT. So it's also the same type of regime. We see all this prof dependence. We also see the broad thermogramming, calorimetry, all these things. And we also know that the kinetics are fast, right? It's in the microseconds time scale as well. So we decided to do further experiments. So we put the dyes at the ends on this protein. This protein is also about 60 residues, similar size. And then we also look at the temperature dependence because we wanted to slow down the kinetics as much as possible. So in this case, we decided to look at the process at 288 Kelvin. And we needed 3.5 molar urea to be at the midpoint, right? Half the nature, which is right there. Okay. In T-jump experiments, we could see that the relaxation time for this protein at that temperature is on the order of 130 microseconds. So a little bit faster than BBL at 5 degrees, but still relatively slow, slower than lower temperature, a higher temperature, sorry. So now we could do the experiments, single molecule experiments. So these are some examples of the type of data that you get. These are free diffusion experiments. So basically what I have here is the strip of photons coming with red and green, depending on whether it's donor or acceptor, as a function of time for the time that the molecule is actually passing by, okay? And this is the index of the photon. So that tells you that for this molecule, we're getting something like 110 photons, and then it goes away. For this molecule, we're getting something like 150 photons, and then it goes away. And all of those are similar. So that's the window that we have, all right? So we have a window that is about 120 photons on average, and typically corresponds to things between 300 microseconds to 900 microseconds. So we don't have the count rates that we had before, but it's still reasonable. So we did the analysis, and this is the analysis with this model that I told you about. We used something, a lot of data together, and we fitted all the data to try to get information from this histogram. You can see the histogram here is really broad. It looks like it has two peaks, right? And people will say it's two-state, and you just don't resolve them well. The question is this shot noise and broadening, or this is real probability for the molecules being there, meaning a small barrier? So from the analysis, actually using something like 8,000 different photon trajectories, each one with something like 100 or 150 photons, we fitted all of this together, and the probability distribution that you get is this blue one, which tells you that all of this is noise coming from blinking, and some of that as well, and also some distortions here from the experiment. When you convert this into free energy surface, you get a barrier that is very, very small. We are not exactly at the midpoint, because obviously we were kind of eyeballing this. But this is still relatively close, because you can see this is less than 1 kilojoule. So we are in probabilities that is like 60-40. Now, the nice thing that you can do about this now is, of course, we have this free energy surface. We have these photon strips. Now what you can do is try to convert these photon trajectories into state trajectories, which is basically trying to find the most likely state trajectory that gave rise to that particular photon trajectory. So you can do this with this type of analysis, which is also coming from Szabo. And in this case, what it uses is the Viterbi algorithm. And it's just basically, you can say, I'm not going to go through this. It will take a long time, but unless somebody's interested. But the basic idea here is what you're trying to do is, knowing the photons trajectories that you have and knowing the model that fitted to it, you try to find out what's the most likely state trajectory that gave rise to that photon trajectory. Okay? And let me just show you two examples, and with this I'm done. These are two trajectories. This is the data. So red and green photons as a function of time for this one and this one. And when we convert this using that algorithm into state trajectory, we have this, in which we have 100 species in the model. The 100 corresponds to fully native, and the 0 or the 1 corresponds to fully unfolded. The minima are over here and over there, and the barrier is this area here. So what we're saying is a molecule here that seems to be in the unfolded state fluctuating, and then is transitioning to the other side, staying in the native state, and is going back. So we can actually resolve the transition path, but you can see there's only a few photons in there. And this is another type of trajectory like this, in which you are going from unfolded, you are going to the top of the barrier, and rather than going forward, you actually decide to go back. So you're actually retracting, and then you try again, you stay there a little bit, and then you jump. And in this case, we have a much longer trajectory. So this folding transition path is much longer than this one. And this is just an example, but the idea is that with this type of analysis, and this type of experiments, we should be able to get this transition path data in a way which is one step beyond what Eaton has been doing so far, which is basically trying to estimate the time. Of course, you have to bear in mind that these are not, we don't know for sure these are the real trajectories. This is the most likely trajectory in states, right? But still, it's as close as we can get to this. Yeah. Another pathway? Well, it's a maximum likelihood analysis, right? So already what you're getting is the most probable thing. And estimating anything else is pretty hard with this type of analysis. So you can get the most likely trajectory, but getting distributions of behaviors, it is no easy way to quantify that. Mhm. Yeah, I mean, the hidden part is that basically, there are many ways of doing the same thing. You can just define the one that is most likely. And this is the caveat of the process. Okay, so this is why you cannot believe completely these trajectories. You can, these ones are, are obvious data sets. These trajectories are kind of made up in a way, but they are the most likely ones. And I think if you can get a distribution of those, in principle, what you see, and we've done that analysis, is we get something that is narrower than the truth. So, if we take these state trajectories for the 8,000 photon trajectories, and we try to get this back, we don't get it. We get something sharper. Why? Because we're implicitly assuming that all the maximum likelihood thing works, which means that your entropy is reduced by definition, right? So I don't think you can use this method to try to get distributions of transition paths, but you can definitely get some idea what the timescales are in a way that is not so dependent on the count rate and also not so dependent on the noise. But yeah, you have to be careful with these trajectories because they're not real. Any other question? Yeah, so maybe too much experimental details. Most of the people here do experiments. But I thought that this way you could get an idea what the problems are when you are on the other side of the barrier, in this case of the problem, which is, you have to worry about analysis, noise, interpretations, and things like that in ways that are different to when you're doing simulations. Although the analysis of simulations is kind of similar in many ways. So. Yeah? Mm-hmm. Yes. But, you actually do that or you don't do anything. So, it's a choice. Yeah, I mean, it's a problem. And this is why it's very important to have controls, that your dyes don't seem to be perturbing the system in a big way. This is why doing bulk experiments first, to make sure that your dyes are not interfering with the process. And first of all, you can design the positions for the dyes so they are not very disruptive. Like, for example, in our case, we put them in tails, long tails, right? Oops, I went too far. Right, so, we actually build a little polypeptide tail, which is flexible, and then we put the dye. So we try to minimize the contact with the structure. And then the other thing that we do is we check that this protein with the labels has the same thermodynamics for folding than the protein without labels. And if it does, it's a relatively good control that the perturbation is sufficiently small. But this is not always true. Sometimes you do this experiment and then you check, and your protein is behaving in very different ways. And most people that do these experiments don't check. Okay? And if they don't check, you don't really know. But, this is the hardest part of this. I mean, the experiments seem complicated, and they are. The analysis is complicated also. But the hardest part is doing all the chemistry and making sure that you put these dyes there, and that they didn't screw up the protein. And that's why most people actually don't, skip that process and then take the experiment and do it. But you have to do it. I mean, this is like, let me just go back here. So, I think I went quickly through that, so maybe it wasn't. Yeah, that's what this experiment is, right? This is here we are using circular dichroism on the unlabeled protein, and we are doing the chemical denaturation experiment with guanidinium and with urea. And here we are doing exactly the same experiment on the labeled protein. They are virtually identical. So that's this is very hard to get. But when you get it, you have, the best approximation to a non-perturbed system that you can have. But you're right. I mean, this is always an issue. The error bars, well, these are coming from single measurements. So I can give you fitting errors. The fitting errors are less than 5% on both of them. So, which also the fact that you get them to be so similar within that noise or within that uncertainty. The main problem here, the main error here doesn't come from the variation in the data. It comes more from the analysis itself, from all these baselines and all this business. So that's why I think it makes more sense to quote fitting errors in this case. Yes? It's only one for all of them. It's a constant transition, diffusion coefficient. The data. Mm-hmm. It is. Yeah, so this diffusion coefficient is the same for all of them. It's just one parameter. And that parameter is picked from the data because the idea is that the time between photons is relatively short compared to the dynamics of the process. So you can still, but still you can see, the molecule is going to move even with one minimum. It's fluctuating. And from there you can get the diffusion coefficient well because, you are not jumping over barriers and you still see dynamics going on. But that means that you have to have a system in which your time resolution is better than the, than the dynamics of the protein. And this is why it's important to do experiments at low temperature, because that way we can get close to that. Yes? Yeah, this model has 3 parameters. Diffusion coefficient and the 2 delta H's that determine the shape of the surface. Just 3 parameters. So it has a whole bunch of stuff here, but it's only 3 parameters. So it's only 1 parameter more than a 2-state model. I had 101 species of states. I could do it with fewer, but then obviously the jumps wouldn't be diffusive anymore. They will be more like kinetic transitions. And yeah, it's possible, but I don't think we gain anything. We tried. No, because what happens here is, since you are putting a lot of data together, lots of trajectories, you are sampling all the possible positions. And what you really want to have is to make sure that jumps between states are faster than your dynamics. So if you make larger steps, then you start mixing, right? So you go into this region in which the 2 things are mixed. So you want to go one stream or the other. Or you can do it way faster or slower, but not in between, because when you do it in between, then you produce perturbations. Not even. This is even simpler. This has no structure information whatsoever. This is purely phenomenological. It's for the analysis of data. It's similar to 2-state model, but the nice thing is that it doesn't assume it's 2-state. It just allows you to have barriers going all the way from one to the other. It's a super simple dinky model, but it works pretty well for lots of things. I mean, it predicts rates with only size. It analyzes calorimetry, and but there is no structural information here at all. So I get the surface from here, and then I get somebody like you say, okay, what kind of molecular model produces something similar. Sure, but you go to higher temperatures, then the kinetics are too fast. Hmm. Yeah. Push it. Yeah, I mean, with this type of experiments, it will be very hard to do. I think you can do that much better with mechanical unfolding. Yeah, it has other caveats and it has other advantages. So in one case, you have these big fluorophores, these photon statistics. In your case, you are obviously tethering the molecule and pulling in one direction. But in that case, it's much easier because you could actually be recording and you could eventually, a little bit, completely different thing. Here, it will be very hard to do. Yeah, because also, you don't get this until much later on in the process, right? So you're not seeing things on the spot, right? So you're getting these photon trajectories. It's very hard to make sense out of them by eye. So it's not until you do the whole analysis with lots of them that you actually get information out of this. So it would be very hard to know where you are in real time. So, it still has lots of limitations. The big advantage, as I say, compared to what people are doing nowadays is this thing that you don't have to bin. Because when you bin photons, then, it becomes a mess. Yeah? Mm-hmm. No, we haven't done that yet. As I said, what we did is to actually look at the distribution of all the state trajectories, the maximum likelihood state trajectories, and what we saw is that it doesn't recover, as I said before, the original distribution. So that means that it's biased. But it'd be interesting. But this is a very simple model. Remember, there is only one pathway because it's one-dimensional, right? So the only differences are going to be, how much is jumping, whether it's staying there longer, and things like that. So most likely, the differences are going to be mostly on the dwell times, with basically on the bottom of the minima, not so much on the barrier, because the time it stays there is not that much. Right? So basically, when we try to reproduce the surface from these maximum likelihood state trajectories, what we see is that the barrier is fine. It's just the minima are much sharper. Which is kind of counterintuitive because you would think that it should be the other way around. But I think it's just because, since you are always enforcing the most possible trajectory normally tends to be one of the shortest ones, right? Yeah. Question is, I'm not sure how far we should go with this analysis because, when I saw these big biases in the distribution, I say, okay, maybe it's not such a great idea to make a big deal out of these trajectories. But I say it's useful from the point of view that it allows you to see, okay, how many photons you actually have in the process, right? How long it takes. I think from that point of view, the analysis is probably fairly accurate. Looking at more complicated things is probably asking too much.